Hello everyone. In this tutorial session, we are going to talk about two topics. The first is special function and another is series function. So first of all, for this course, we need to know about the definition and the properties and the calculation of the special functions. So a special function are type of function that you cannot represent them with elementary function. They are important, so we want to study their properties, so it may help us to calculate them more easily. So first of all, let's look at gamma function. So gamma function has a definition like this. Gamma function of p equals to the integral from 0 to infinite of x to the power of p minus 1 times the exponential to the power of minus x dx for p larger than 0. And it has some important properties. First, there is a recursive relation. That is gamma p plus 1 equals to p times gamma p. Another is you can calculate it. Actually, we can calculate it. Gamma of 1/2 equals to square root of pi. The third property is for any integer n, the gamma function of n equals to the factorial of n minus 1. The fourth one is, and the last one is gamma p times gamma 1 minus p equals to pi over sine p times pi. So till this point, what we know is first we know gamma's value at some point. For example, 1, 2, 3, this kind of integer, and 1/2, etc. And we also know their recursive relation, etc. So what we need is to use this relationship and this value at certain points to calculate some integral. For example, if we want to represent integral like this, then we can just write down the form and solve it like this. And this is all about gamma function. Another important special function is called beta function. The definition of beta function is more interesting. One important form looks like this. beta function of p and q is the integral from 0 to 1, x to the power of p minus 1, 1 minus x to the power of q minus 1 dx for p, q larger than 0. So there are some important properties. First is the equivalent definition. So with change of variable, we can have some important form of the beta function. They are equivalent, but then look quite different. For example, if we use change of variable like y equals to ax, then we can have pq equals to this. Let me rewrite it. 1 over a to the power of p plus q minus 1, 0 to a, y to the power of p, a minus y to the power of q minus 1 dy. Minus 1. Another equivalent form is 2 times pi over 2 sine theta 2 times p minus 1 times cosine theta to the power of 2 times q minus 1 d theta. The last form is integral from 0 to infinite y to the power of p minus 1 over 1 plus y p plus q dy. Okay, all these forms are equivalent and depend on our function or the integral. We can use different form to simplify our calculation. And a second property of it is symmetry. That is, bpq equals to bqp. And the last one is its relation with gamma function. So since gamma function has some very interesting and useful recursive relationship, if we can find a relation between beta and gamma function, we can use those gamma functions property in beta function. So bpq equals to gamma p times gamma q divided by gamma p plus q. Okay, now let's look at some example. So for example, like this, integral from 0 to 1, x squared 1 minus x squared to the power of 3 over 2. So for this, we can first use change of variable because there is x squared inside the bracket, which make it hard to represent in the gamma functions form. So we use a change of variable. So change of variable, x squared equals to y, and therefore dy equals to 2x times dx, and dx equals to 1 over 2 times the square root of y dy. Here you should notice that we need to replace all the x with y. So there is x here, here, and here. We need to replace 3 of them. So we know x squared equals to y and dx equals to 1 over 2 times square root of y times dy. And then this equals to, so by letting y equals to x squared, the range of the integral did not change because it started for x equals to 0, y equals to 0. For x equals to 1, y equals to 1. So the range of the integral does not change. It becomes like this. And if we continue, we can get this. Now, this is the form we are looking for. So this is the basic definition of beta function, which equals to 1 over 2 times beta 3 over 2 and 5 over 2. And if we use its relationship with gamma function, we can get more explicit result. So it's gamma 3 divided by 2 times gamma 5 divided by 2 times gamma, add them together, which is, so here this one equals to, and the second one is just do it twice, use a gamma function's property, do it twice, and the denominator is gamma of 4, and it equals to 3 over 16 times 1 times 2 times 3 over gamma square. So cancel 3, it's pi over 32. So this is this example. We first use change of variable, and then we construct the form in beta function. And then use recursive relation of gamma function. Okay, now let's continue. Let's see another example. For example, if we want to calculate the integral from 0 to infinite of y squared divided by 1 plus y to the power of 6 dy. In this case, we want to use the form of this. And we have p minus 1 equals to 2, p plus q equals to 6. We got p equals to 3, q equals to 3. Therefore, what we need to calculate is actually b33. It equals to gamma 3 times gamma 3 divided by gamma 6, which is just factorial of 2 times factorial of 2 divided by factorial of 5, which is just 1 over 30. So this is a fairly simple one with gamma and beta function. Otherwise, it took lots of effort to calculate it. Okay, let's see a last example. So this example is integral from 0 to infinite y times dy divided by 1 plus y to the power of 3 squared. So here we want to also use the form that we used here, like we also want to use this form, but there is y to the power of 3 here. It makes the calculation not so obvious, so to make it simpler we use change of variable. Let x equal to the power y to the power of 3. Therefore dx, and therefore y equals to x to the power of 1/3, and dy equals to 1/3 times x to the power of 2/3 minus 2/3 dx. Notice that since we need to use change of variable, we need to change this, and this. So y equals to x to the power of 1/3, dy equals to 1/3 times x to the power of 2/3 minus 2/3 dx, and y to the power of 3 just equals to x. So we got all of them, we can assemble them together. So it equals to integral from 0. So since x equals to y to the power of 3, so when y equals to 0, x equals to 0. When y equals to infinite, x also equals to infinite. So the range does not change. We have this. And move 1/3 outside, we got x to the power of minus 1/3. So we have p minus 1 equals to minus 1/3, p plus q equals 2. So p equals to 2/3, q equals to 4/3. Now the original integral now equals to b 2/3 4/3, and it equals to use the relation with gamma function again. It equals to gamma 2/3, gamma 4/3, and gamma 2. So gamma 2 just equals to gamma 2 just equals to 1, so we can ignore this, and it just equals to, there's 1/3 here. So 1/3 here, gamma 2/3 times gamma 4/3, and gamma 4/3 equals to 1/3 times gamma 1/3, so it's 9/3 times gamma 2/3 times gamma 1/3. It equals to pi over sine which equals to and this is 2 times square root of 3 times pi divided by 27. So with this example, we see that to calculate integral with beta and the gamma function is very useful, and usually we need to use a technique of change of variable. So this is all about special function. Another topic we want to cover is series function. So series function is series function, you can consider it just as another way of representing a function. So, for example, for this typical function, exponential function, it can be expanded as a power series like 1 plus x squared divided by factorial of 2 plus x to the power of 3 divided by the factorial of 3, etc. And another example is sine function. It can be written as x minus 1 to the factorial of 3 times x to the power of 3, etc., etc. And if you have a polynomial, for example, x minus 1 to the power of 2, you can just expand it as a polynomial, like this. So this is one way to consider series function, and then that power series. And another way is you can actually generate new function with series. For example, if we define a function like this, summation from 0 to infinite of x to the power of factorial of n for example, x equals to, in the range of 0 to 1. This is interesting because, first of all, this function is convergent. So why is that? First of all, x is positive and less than 1, and this function is convergent, right? Because it actually equals to this. So this function is definitely convergent. It's convergent to this. And this is just a subset of this. And which means it is smaller than this because x is positive. So it is definitely convergent. So this is another function. The thing is, we can write it easily with power series. Can we write it down in an elementary form? Like, for example, in a form like this, a combination of elementary function, for example, sine function, cosine function, exponential function, log function, etc. Can we do that? Maybe, but I don't know how to do that. And I searched online. I didn't see an example how to do it. That means with power series, we can generate new functions that are hard, or if not impossible, to be represented in elementary functions. So that means series are powerful tools for us to solve equations, because solution to some equation may be very complicated if you want to represent it in elementary function. For example, x function, x cosine x squared, these kind of things. But if you represent it in power series, it might be easier. So let's see an example. How to solve equation. With power series. The step looks like this. First, we assume y equals 2. So we assume y have a power series expansion look like this. an times xn, summation from n from 0 to infinite. And then we can calculate like y prime equals to something look like this, because the n equals to 0 has been cancelled due to the derivative. So we have n minus 1. And as a second order derivative, looks like this. N minus 1, n to the power of n minus 2. And then we plug in this representation into the equation. For example, I just randomly write a equation equals to xy, for example, look like this. And then we try to find the representation of an as a function of n, or just an's recursive relation. And then lastly, we plug it back to y equals to summation from 0 to infinite of an times x to the power of n. So this is the outline of how we use power series in the scenario of solving the equation. And we can see explicit example. So for example, if we want to solve an equation look like this, x times y prime equals to x times y plus y. So this equation is super easy to solve with, separation of variables, things like that. For example, it's look like dy dx equals to 1 plus y, and y with separable method, we got this, and just doing an integral, we got this. X plus log x plus some c, and therefore we got y equals to some exponential of x plus log x plus c. So move log c, exponential of c to the front, and we got times x times exponential of x. So you can just consider it as a constant a. It's super easy to solve, but this is not the purpose we want it. What we want is to solve it, for the purpose of this course, is to use the power series to solve it. Okay, let's see how can we solve it. So first we assume y have a power series expansion look like this, summation from 0 to infinite, x to the an times x to the power of n. Then y prime equals to, so with n equals to 0 is a constant term, and with derivative is cancelled, so times n to the power of n minus 1. So this is the derivative of y. So here we have this term, and this term. We need to calculate them explicitly and then add them together. So this term we also already know, and this term, x times y prime, it equals to 0 an times n x to the power of n. And xy, it equals to n equals to 0 to infinite an x to the power of n plus 1, because there is x here. So now we have some we have all the elements we need to solve it. So the equation is x prime minus xy minus y equals to 0. So we got this is the first term is summation from 1 to infinite an times n x to the power of n. The second term is n equals to 0 an x to the power of n plus 1. So here we can use change of we can shift the index by 1, so it is n equals to 1 infinite a minus 1 x to the power of n. So this is equivalent. We just use this shift to make our notation easier. So plus and minus summation from 0 to infinite an times x to the power of n equals to 0. Or we can write it down like this: minus a naught plus summation from 1 to infinite n times an minus an minus 1 minus an times n x to the power of n equals to 0. So with this, we can compare the coefficient of both sides of the equation. 0 can be viewed as summation from 0 to infinite of 0 times x to the power of n, right? So here we need to have the coefficient of the same polynomial to be the same, for both sides of the equation. So minus a naught equals to 0, and n times an minus an minus 1 equals to 0. Now, last step is a little bit tricky. So we know a naught equals to 0, and if n equals to 1, then a1 minus a1 minus an minus 1, which is a naught, equals to 0. It gives us nothing because it tells us minus 0 equals to 0. So the first equation gives us no information. That means, okay, the first equation gives us nothing. No information. That means a1 is a free constant. They're just like a or c1, c2 in the in a general solution of other function. So if n is larger than 1, then we have n minus 1 an equals to an minus 1, or an equals to this. So this is a recursive relation. If we write a few more steps, we got something like this. It's 1 an minus 2 n minus 2 blah blah blah. In the end, it equals to n minus 1 factorial times a1. So it is a very interesting cases. Now we can put them together. Y equals to n equals to 0 to infinite a1 factorial of xn, and 0 is equals to 0, so it looks like this. And if we write it down like this, this term is exactly the exponential function, so it equals to this. Okay, this is everything for today. If you have any question about it, you can raise your hand in the Zoom, and I will